Hi, hello everyone. I think we still have some students joining, and we will wait for maybe 2 minutes and then we'll begin. Yeah, so a student asked whether we will, uh, like today we will finish this slide, right? So can you do quiz 3? The answer is that we have 2 slides for data link layer, so you can already do quiz 3. Okay, so the quiz are, I think, the latest quiz release. And finishing this slide, we will have a quiz 4. Okay. And there's another question. Oh, the midterm will be early March. Okay, so it's a week of early March. I will let you know by the end of February. And it will not be so difficult. Okay, so it will be similar to quiz, but a little bit different questions, but to test to understand. Okay, we will go over what we will be testing. Okay, we should begin. If you have any question, feel free to ask. So last time we have seen that we needed this exponential backup, right, in our protocol, because on the shared media, if both people here they are talking to each other, right, the host find some conflict, okay, so both should stop, okay, and the backup for a random amount of time. And so in order to detect, right, so let me see what we can do this. Okay. So we have host A to host B. When you put the first bit of the frame onto the Y, okay, host B will not hear it already, right? So host B may also be sending something, but it will finally propagate to your side, okay, right? So if you don't allow enough time, right? So maybe your packet is already out when you hear B, okay? But if you have minimum packet size, then you will hear, hey, B is, so the propagation time is covered, and the B is corrupting, so corrupting my packet. So you can like retransmit this packet, okay? You can back off. For this reason, we need a backup timer, which are actually set in the unit of this number of bits. Okay, so and our minimum Ethernet packet size is also this number of bits, okay, 64 bytes. The reason we need this is because we want to wait for, we will be able to detect the collision, okay, from the other side. Okay, and last time we did a calculation that it can support 6,400 meter long wire, which is very reasonable, right? Usually in your local area network, you are not using a very large Ethernet link, okay? And you cannot use so the basic unit is 512, right? You cannot use less than that, okay? The reason is very simple. If you use less than that, then probably you are already put things on one, right? So even if you back off, right, you wait, okay, you will be sampling. You can sample 1 instead of 100 of this time step, right? If your 1 is within this number of bits, maybe you are sending something, but you could get corrupted, but you cannot detect it, okay? So the waiting time should be the unit of 512 bits. This is what we discussed last time. And besides the minimum packet size, there's also a concept of maximum transmit unit. Okay, as the name is called MTU, and when you look at the terminology of the networking, you will frequently find the concept of MTU. So this is the maximum transmission unit passing your network. Okay, so you cannot go beyond that. If you have more than that, you need to decompose into multiple smaller packets. Okay. So why do we want to have an upper bound on the packet size, right? So previously we explained why we need a lower bound, right? Because we want to be able to detect the other people are talking, and it takes some time to propagate to me, right? I want to detect it before I fully finish the packet. Okay? So we also need a maximum transmit unit. This is because bit errors in long packets will incur very high recovery penalty. Because you think about it, if just one bit in an entire packet is wrong, I will drop the entire packet, and I will not just drop one bit or the half a packet. Okay, so that means if you have a very long packet, let's say a movie of 10 GB, okay, and you have some bit that is flipped, okay, and the whole movie would, so maybe transmission takes maybe half an hour. Then you need to retransmit again. So this is obviously a bad idea, but that's extreme. Okay, just give you some idea. So we don't want a very big packet, okay, because the cost of a bit error is too high for retransmission. But again, solving this with an upper bound of the packet size called MTU is okay, but there are also some overhead. Okay? So firstly, we know that there are some bytes that are wasted, right? So you know that each time we need some headers, okay? We need some headers, and this header actually occupies your whole packet size, right? So for each packet you need to have certain headers, like the MAC address for the source and destination, okay? And if you split a moderate sized packet into many of them, right? So each of them you need to attach this MAC address. Okay, then you kind of your useful payload is a bit low. Okay, and there's another problem, right? So packets are processed one after another, right? For example, if we have a, let's say, hub or switch, right, we'll check your MAC address and then decide where to go, okay? Right, so this is actually having some processing overhead. Like those devices need to read your MAC address, right? If you have multiple packets coming in, right, the processing of the header also takes time, or maybe also the checksum, okay? So you can see that for data centers, right? So it's pretty safe. I mean, and the bandwidth is pretty high, right? So having so many headers will be very wasteful. Okay, so there's a concept of jumbo frames in data center, where instead of the maximum size being 1,500, right? Say allow 9,000 bytes per packet. Okay, it's like a 6 times the original upper limit. Okay? So in data centers, we allow much larger. Okay, because transmission is very fast. Everything is in high speed now. Any questions? Okay, so far what we talked about is that every host just using like a T connector, or using some hub to connect to. You can look at them as connecting the same piece of wire. Okay, the same piece of metal, right? And propagating light speed. There's some delay, but very fast. Okay, but today's Ethernet switch is totally different. Okay, so it's by switch, which means if A is talking to B, let me give you an example. Okay? Assume we have a switch with 4 ports. A is talking to B, and C is talking to D. They can transmit at full speed. Okay, so it's 1 Gbps. Okay? So you can transmit basically, you can transmit full speed 1 Gbps, and this is 4 duplex, right? So you can also talk in the other direction 1 Gbps. Okay. Similarly, C can talk to D 1 Gbps. D can talk to C 1 Gbps. Okay, so something like this. The only thing that can incur conflict is, for example, A want to talk to D, and B also want to talk to D. If that happens, maybe each one have half the bandwidth, right? 0.5 Gbps. Okay, so this is what the switch, right, is accomplished, right? So basically, this piece of media is no longer, it's still shared, right? It's still a subnet, but it's much more efficient. Okay, as long as you are not too many people are talking together, right? You are sending to everyone, or you are receiving, right? This is the sender receiver side bottleneck. Otherwise, if there's no such conflict, okay, you can just send whatever you want, right? Because of this reason, there are also, if you know, like MPI, those kind of methods, right? So there are methods to propagate packets, right? When you are broadcast something to this guy, all right, this first round you probably can only do this, right? Because you only have one outlet. Okay. Next time you can propagate another guy. This guy can get the same count to another guy, right? Next time these people can propagate to other people, right? So there are some algorithm to really do the broadcast more efficiently. But keep in mind that each time you just send a packet to one person using 4 bandwidth. Okay, right. So there is something like this. This is designed for the switched Ethernet structure. Okay, let's continue. So now, if you look at the default Ethernet configuration anywhere, okay, including the device UBA, right, Ethernet switch, it will be 1 Gbps speed, okay, 1 gigabit Ethernet, right? So if you using cloud, you also by default you are connected using 1 Gbps Ethernet, right? But you can choose a high-end one, right? So 10 Gbps, right? This is because their Ethernet switch is more expensive, right? So then they can support higher speed, 10 times speed. I believe in data centers, you think about there's different racks, right? In between racks, your bandwidth should be much higher. So actually, it's not uncommon to see like even 100 Gbps links. Okay? But usually, most accessible one are 1 Gbps, but high end is 10 Gbps these days. Okay, very accessible. And so they are basically using the same packet header that we talked about, right? So there's a MAC address, checksums, this kind of stuff, right? And padding for them, okay? And this is a 4 duplex, right? So I just explained what it did, right? So as long as you are not sending to the same person or not so you are not like A sent to B, C sent to D, right? As long as sender and receiver are different pairs, you can have them together, okay, at 4 bandwidth, like 1 Gbps, right? And the reverse direction is also the same, okay? A is sending 1 Gbps to B. In the meanwhile, B can also send 1 Gbps to A, right? It's like you are exchanging or removing. And so there's also a process called auto negotiation, right? So for example, if you have a subnetwork that needs expanded, right? And the previous one is 1 Gbps. Now you have a 10 Gbps. Right? So you know that a lot of things parameters are different. For example, if you look at the NTU, right, it will be a little different. Okay, and also the packet, million packet size will also be a little bit difficult. Okay? Different, but they can communicate, right? So, but there's some cost, right? So basically, 10 Gbps packets will be downgrade to 1 Gbps packets. Okay, but they can negotiate to communicate. And now Ethernet can also provide power, which means you don't need a independent power connected. Let's say you have security camera, right? You can just hook up to the Ethernet, right? So you just need a one wire structure to get your camera working. Okay? You don't even need a battery. Okay, so this is because Ethernet itself can carry power. So far, we talked about Ethernet, right, which is a wired connection. Okay. Next, let's look at the wireless one. Right? So a wired connection is called that's IEEE standard called the 802.3. Okay. Wireless is 802.11. Okay. Whenever you see these two numbers, you know one is Ethernet, another is wireless. Okay. So this is Ethernet. Okay. 3 is Ethernet. And there's a lot of other protocols, of course. But so this is 802.11. Okay. When you see 11, then it's Wi-Fi. Okay. Next, let's look at what's the difference between wired and wireless connections. Right. Ethernet has only one shared collision domain. Right. So because you think about it, right. So you have a same piece of metal everyone connecting and transmitting signals. Okay. Right. So all hosts on a LAN can observe the transmission. Okay? This is light speed, very fast. Of course, you need a minimum packet size of 64 bytes, but that's all you need to take. Okay? But wireless is different, right? So the radio signal is propagating probably a little bit slower much slower than light speed. Okay, right? And it's a wave, right? Depending on the wavelength, how fast it can propagate. Okay, so. And another important thing is that these radios, there's no guarantee of delivery, right? So the signal will be weakened every time it propagates further, right? Because it's a space, right? 3D space. It become weaker along all the directions. Okay. So they all have very small ranges compared to the overall system. Okay, so this will add a lot of complications in our problem. Right, we will discuss what are the complications. Okay, so firstly, collisions are local. Right, so what does this mean? Right, so for example, you have wireless connections here. Right, this guy can only reach maybe here. Right, so you cannot reach here. Right, so you can think about they are talking, they will never collide. Okay, only locally you can collide with people in your range. Okay, so this means collisions are local. And collisions are a receiver, not sender. So what does this mean? Okay, let's go back to this example again. You have 3 people, right? And it's 3 people. Okay. Right. So maybe let's say 2 people are here, and this guy is sending to this guy is sending to this guy. Okay. Right. So you have 2 signals. Right. So one signal is one packet is like this. Okay. And you know that you can reach this guy. Right? The range is something like this. Right. Okay. But you cannot reach there because there's some distance here. Okay? And we have another example where you send let me change the color. You send a message to this guy. Okay. But your range is something like you haven't reached this guy yet. Okay? So seemingly, if you let the sender do the detection, right? The sender is here, do the detection. You will find, hey, this is within the conflicting range. Okay, so maybe if you want to drop it, like in Ethernet, right, and back off, you as a sender. Okay, you can do that, but that's not necessary because here the red signal doesn't reach here. Your receiver will receive the correct signal. Similarly, the green signal will not reach this here, right? So your receiver actually can pass. Okay, you don't really need to back off here. Okay, so this is the intuition. And we will see an animation later. Okay, it's giving you some idea. Finally, carrier sense, which shorthand notation CS, right, plays a different role. Okay, so because now we are not back off by the sender. Okay, so we are just listening. We will see what's the difference. Okay, so here we use a so-called concept of collision avoidance, right? So not CD, right? Detection by the sender and then back off. Now we are choosing another solution, avoidance, right? So think about what can you do, right? So the best way is you just send something. Now that the sender don't know, even if I hear other people talking, but maybe my message will still deliver to my receiver because the other person is not talking loud enough, will not reach my receiver, right? So the only way is you wait for the receiver to acknowledge your packet, right? So that's what what it means, right? But you do want some avoidance, which means if you know that you are talking to that receiver, right? So you want to tell other people within your range not to talk. Right? So let's continue. So here we are illustrating this concept in a wireless environment. This is a very famous term called hidden terminal problem. Okay, so what is a hidden terminal problem? So this is basically what we just described earlier, but here is an animation, so we can recap of this. Right. So let's say A and B both want to send to A and C both want to send to B. Okay, and because A and C may be too far away from each other, they cannot hear each other. Right. So this is a reverse. You think about it, right? So because it's a reversal of previous example, right? Previous example, we are saying that if you send, maybe even if there's conflict, you detect. Maybe the receiver will not have problem. Here it's something different, right? Maybe A and C are sending, but they cannot detect each other, so they don't know the collision. But here B can still fail. For example, if you think about A and C, their range, okay? A cannot listen to the purple signal from C, right? C cannot get the red signal from it. So literally, they simply think there's no collision, okay? But they arrive at B together, B will be collided. Right? So again, you have to wait for the receiver to acknowledge. Okay? So this is called a hidden terminal problem. You cannot detect anything, right? So you have to rely on the receiver to tell you whether you're collision. Okay? So to A, C is a hidden terminal. To C, A is a hidden terminal. Okay? So hidden terminal means that the sender side collision detection, which means you hear somebody talking, you back off, it's useless, right? Because even if you back off, you cannot hear C, right? You don't back off, right? You just can continue, okay? So the other problem is what I just described earlier, right? So this is called exposed terminal problem, okay? Right. For example, this is showing that the carrier sensing has some problem. So for example, A is sending to, B is sending to A, C is sending to D, right? But A and D can still just get one packet. This A got the red one, the D got the purple one, right? But if B and C are sensing the air, for example, right? Sensing the air, so then they will think they are conflict, right? And they back off. It's not necessary. Okay. So that's the complication, the two complication problem caused by, the wireless environment. Okay. So for example, A, right? A can B. So a better problem solution is this. Right? For example, B is sending a message to A, right? And then C, if it's listening, it will think, hey, this channel is busy, right? C will not send to D, which can happen in parallel, actually, concurrently. Okay? So basically, the carrier sense can erroneously reduce the utilization because C can send to D anyway, but it will not do so. Okay? If you just do the carrier sense. Okay? So why is there so much complication in the wireless environment, right? So the wired environment, you can think about everything is connected in one piece, okay? Right? If A can send a message to B, B can send a message to C, then A can also send a message to C, okay? Right? It's the same piece of metal. Okay? Everyone will hear the message, right? But the wireless signal will be weakened along all directions, right? So it's maybe cubically, right? Reducing. Okay? So the range is very small. Okay? And so the reachability in wireless is not transitive, which means, for example, if A can reach B, B can reach C, it doesn't mean that A can reach C. Okay? Here's the example. Right? A can reach B, B can reach C, C can reach D. But A and D, for sure, they cannot reach each other. Right? So there's a protocol proposed for the wireless environment called multiple access with collision avoidance. Right? So this is one version. Right? So the collision avoidance can also be used with CSMA protocol called CSMA-CA. Previously, we talked about the Ethernet protocol. It's called CSMA-CD. Okay, let's look at the simplified version, which is the MACA. Right? So it's a multiple access with collision. Okay, it's developed very early. And here's how it goes. Okay, so basically we will first let the sender sense the channel. Okay, and the sender, if it thinks the channel is not busy, right, then the sender can send a so-called soft reserved channel. Okay, the sender can send an RTS. RTS is request to send. Okay, and then so here what we have some context. So what we are sending, the packet, should be sent from the sender to the receiver. Okay, right? These are other people. Okay, right? But the packet is the MAC address. Source is this, destination is this. Okay, so this is what we are looking at. And so when receiver find, hey, this packet comes in, and I'm the destination, I will send a so-called CTS, clear to send. So which means, hey, now you are able to send. Okay. And then the sender, once receives this clear to send message, the sender will just send the data. Okay. So yeah, so the RT is the request to send, and the CT is clear to send. Right. So, but there's something that can happen. Right. So this is called soft reserved channel. Okay. And you think about it. So this guy is in the receiver's range, not in the sender's range. Sender can have no way to detect this guy, right? And but because the receiver, right, will be receiving something, okay, it will send a clear to send. So the sender will send stuff to receiver. Okay? So then this time receiver is busy. Okay, so it need to, if let's say this CTS packet, okay, right, it should be delivered to sender, right? So let's say the destination is a sender. Okay, if the destination is a sender, then the sending, then if the sender receives the packet, okay, it will just continue to send data. But in the meanwhile, if another host in your range receives the packet, okay, it will not send anything. It knows it's busy, right? Why is this the case? This is because if it sends to anyone, it don't have to be your receiver, right? It can send to another host here, right? But it will reach the receiver, okay? This is within receiver's range. Then this signal will be corrupted with this signal here, okay? With this signal here, right? And their receivers, you cannot receive stuff, right? When you say clear, not anyone in my range cannot just send anything, right? Because I want to get this message. If you send something, you will interrupt, you will disturb my receiver, okay? And of course, the sender will send the data to here. It will also send the data to the sender's range, okay? And when this happens, the sender will see a little bit weird, right? So the receiver will see the CTS. It will know, hey, I should not send anymore, right? I should wait until the receiver finish, okay? But the sender's host, the sender side range host, right? It will know that RTS will know someone is is not me, right? Because the sender's packet is to this MAC address, okay? It's not this host MAC address. It knows it's not sending to me, but this is called the software of the channel, right? Okay. And hopefully, if it's also within the receiver's range, I have a CTS. Then it means I truly cannot send, right? I can, because the sender is sending to receiver, I cannot send. But unfortunately, this host is not within the receiver's range, so it will never receive a CTS. Okay, that's why we say this is a software reserved channel, right? So it's not a, because it doesn't know, right? The sender is truly sending to the receiver. Okay. But that's fine, actually, right? Because if you this host is communicating, it will not influence the receiver's receiving. Okay, that's fine. Okay. And when we talked about the receiver's host, now it's holding, because if it sends anything, it will corrupt this packet that is being received, this data, right? So at some point, the receiver needs to say, hey, now I'm done, right? You need to continue, right? So receiver will also broadcast acknowledgement, okay? And so there are also two destinations. Well, one is to sender, right? The sender get it, then it knows that the packet is sent, right? So it's a successful transmission. I don't need to retransmit. I can move on to the next packet, okay? It will also receive other hosts in the receiver's range, right? And this is very important, because then now it's like it's released, right? The channel is released. Now this host can continue to send stuff, okay? So this is very important, right? So it knows the channel becomes idle again. So here, put simply, it's really receiver driven, right? You can see whether it's clear, and then you acknowledge, right? So this is a receiver driven. This is called a collision avoidance, because let me see. Okay. Because this range is avoiding the collision, right? If you get CTS, the channel is occupied, right, until it's idle. Then okay. Otherwise, you will corrupt this data. Okay, so that's called the avoidance, collision avoidance. Any questions? Yeah, just look at this slide and the animations, those concepts. Okay, it should be clear. Okay, so the collisions in Marca is like this, right? So what if the sender does not receive CTS, right? And acknowledgement, right? So this is possible, because the sender, when it can send, right? If you clear, it can send. If you don't clear it, it means maybe the receiver is busy receiving somebody else, right? It's its job. Okay, if that happens, sender has to resend the RTS, right? Similarly, if the data is not acknowledged after timeout, right? The sender should also send the data again, okay? Because the channel is now occupied for sending your data, right? If you don't resend, it will waste everyone's time. Okay? So what if sender does not receive CTS, right? It will assume collision. Basically, maybe if the receiver knows that you have a request, right, it will send a CTS. But what if you reach there, but some other packets or some other people send, right? Then your bits will be corrupted, and the receiver will not know this is RTS, okay? Right, so then it will not return a CTS to you, right? In this case, you can only assume there's a collision on the receiver side after timeout, and you have to send out this, right? But you cannot just keep sending, right? Because other people are also sending, and you are also sending, then this just makes things worse, right? So you also need to enter exponential backup mode, right? But you only do so, unlike if you remember in the Ethernet, we do the backup mode when we listen and we hear somebody is also sending, right? This is carrier sensing. We have a minimum packet size, okay? But receiver side is, here in the wireless environment, you really need to wait for the receiver to respond to you, okay? And only when it's timeout and you didn't hear a response with a reasonable time, you are sure that there's a collision, okay? But you cannot hear somebody, you think it's collision, right? Like what I said, right? So if you hear somebody, you think it's collision, but maybe when you send to a receiver, that collided signal cannot be get by the receiver, and you can send it anyway. Okay? So only when you cannot receive CTS or ACK, right, you cannot get confirmation from the receiver. Maybe the receiver cannot interpret what you were sending, right, because of collision. Then you can enter exponential backup. Okay. And as I said, so there are a bunch of Wi-Fi protocols, right? So standards, right? And here we will discuss some, right? So they all, we are talking from earlier protocols, okay, to the, later protocols. And later protocols will be, uh, faster, okay, because the standard earlier is designed for lower bandwidth protocols, right? The technology is older, okay? And if you go to later protocols, the technology is more advanced, right? A lot of in communications, of course, right? You may not understand, but just to get an understanding, we will be talking about the protocols. Like B is probably earliest, right? So the supporting of the speed is the lowest, bandwidth is lowest, okay? And then we'll talk about AG, this kind of thing, right? So overall, so the Wi-Fi protocol in IEEE, I think the Wi-Fi protocol is, 802.11, right? Ethernet 802.3. Okay, if you remember what we talked about. Okay, so when you see 11, it's Wi-Fi, and yeah, it's very easy to memorize, right? Because of Wi-Fi, right? There are two I's, okay, right? And Ethernet is 3. Right? You can think about 3 is a E, right? So in the opposite side, right? Okay, so some way that you can memorize it. Right? And so the B protocol, right? 802.11b protocol, it's very early. It's introduced in 1999, okay? And it uses a so-called unlicensed band, right? Which is a 2.4 hertz band, right? So it's the same band as, microwaves. That's pretty bad, which means if you are using the B version of the Wi-Fi, right? So if, let's say, someone in the family is using the microwave, okay, maybe there's a lot of collision already, right? So this band is not good, right? So it's in the same band, you are talking on the same frequency, basically, and a lot of interference, okay? And so they are using a modulation scheme called a CCK, complementary code keying, but I'm not sure whether you want to explore a little deeper, right? So if you want, you can, it's communication stuff, right? So you can Google a little bit, okay? And it supports 2 data rates, right? One is 5.5, another is 11 Mbps, right? It's much lower than, than Ethernet for sure, right? Because Wi-Fi is, of course, more difficult, okay? Ethernet, we start with 10 Mbps, and then 100 Bps, right? And then 1 Gbps. Right? Here it starts from a little bit lower, okay? And so the practical throughput with TCP is actually, only half of this 11 that you can reach, okay? Right? Because those collisions, those, we talk about there could be collisions, right? People, if you think about microwave, could be lower, right? I mean, microwave over, okay, maybe the radio signal itself is microwave. And again, so, it has a bunch of channels, right? There's 11 channels that you can use, right? They are operating at different frequencies, okay? But unfortunately, there will be a lot of collisions if you use nearby channels. So it's recommended you only use 1, 6, 11 because they're awesome. Here's an example. Right? So this is 1, this is 6, this is 11. If each host is communicating with a wireless router, one is connected to this, this frequency, another is this frequency, another is this frequency, right? Then you guys can talk simultaneously, have no interference, right? If you use something like 3, then 3 can conflict with 1, and they can also conflict with 6, right? You can see. So typically, if you are using wireless router, it will give you some access points, right? So with different frequencies, right? And maybe speed, okay? Different devices, if you choose different, then it could reduce the competition. Okay, so next is a version of the Wi-Fi, right? So it uses a higher band, which is 5 GHz, right? So it can support faster, higher bandwidth, right? Higher speed. Okay, it can go to 54 Mbps, right? So if you look at the previous one, it's probably just 11. Right? So I think it's blocked. And so this is the newer version, right? And a switch from CCK, right? If you remember, to another modulation method called orthogonal frequency division multiplexing, right? So you see orthogonal, then you know it's much better, right? So it will have less interference. Okay. So the benefit is that each frequency is orthogonal. Basically, if you use a different choice here, right? So there will not be interference. Okay. And then you have the G version of the protocol, right? 802.11g, right? So it's introduced in 2003. And it uses, again, still this OFDM, right? Orthogonal frequency division, right? So to improve the performance, okay? So we call it multiplexing because, they are all sending to the same area, right? So, but they are kind of have some encoding method to make sure the codes are also, okay? And so this will improve the performance, right? So it can reach this highest speed, okay? And it's also backward compatible with earlier B version, the first version we mentioned, okay? But again, because the previous one using CCK and this is using OFDM, right? So there would be a revert back to CCK, which means you cannot fully utilize the bandwidth and the lower confliction of the G version of the Wi-Fi. And then we have the N and AC, right? So the N version of the Wi-Fi is introduced in 2009, and it uses so-called multiple input, multiple output technology, right? So which means, if you see when you buy a wireless router, right, you will see a lot of antennas, right, coming out, right? So usually giving an impression that if you have more antennas, it's going to be faster, right? I mean, the bandwidth is higher, right? So this is starting from the end. Okay, so you can send and receive using multiple antennas, right, per device. Each antenna will provide some bandwidth, right? So you can have up to 4 sender and up to 4 receiver in this protocol. Right? And the data stream is multiplexed across all antennas. Okay. So basically, this allows all antennas to be functioning and support high rate. You can see that the maximum now can reach 600 Mbps, not too far away from the Ethernet 1 Gbps, right? So this is pretty impressive, actually. Right? Of course, you remember we can have 4 by 4, right? 4 incoming antennas, 4 outgoing antennas, right? So sender receiver antennas, right? If you use all of them, right, 4 by 4 configuration, you can reach 600 Mbps, right? But usually, it's more common you only have 300 Mbps. Okay? It's 2 by 2 configuration. 2 by 2 means you have 4 antennas. 4 by 4, your wireless router will be very ugly. Okay, so you have 8. And so the next is the AC version of the Wi-Fi, right? So it's finalized in 2013. Okay, and again, so this means they have more antennas, 8 by 8. Okay, and it can support up to 1 Gbps. It's even if you are using wireless environment, you can see that its bandwidth quite close to the Ethernet, right? So it's 1 Gbps, but it's very impressive. Okay? But it takes some technology. You can see these Wi-Fi technology is very recent, right? In the recent decade for AC and a lot of, at least in this century. Okay, but if you look at the Ethernet, it's a long time ago. Okay. All right, any questions? Oh, I see some question on chat. Okay. So let me see. May I know how long TX will wait before retransmit data after detecting interruption? Oh, so these are some details, right? So so the time, I think it should be similar to the back of the, it's a random sampling, right? So it's exponential backoff. It's the same algorithm. Okay. I'm answering the question. Okay, but there's the smallest unit. Okay. Yeah, I'm not exactly sure, so I cannot tell you right now, but I can check it out. So, but you can also search. I think Maca is a very old protocol, so it could be a little bit different, but you can double check. It really depends on, I don't think it will be this big because, it's an old protocol, right? And for the early radio signals, I think Maca is very, I think it's not this one. Okay, it will be larger, I think, right? So because it's wireless and the bandwidth is not so high at that time. Okay, but you can double check. Right? It need to wait longer. I think. Okay, let's move on. Let me see. So let's look at the market style RTS CTS protocol, right? So you can here you can again in Wi-Fi you can again have the RTS CTS, okay? Which means when you want to send, you can say I want to request and then clear the channel, right? So receiver driven, okay? But that's optional, okay? Right. So you don't have to occupy. You can also send it right away, okay, without clearing. Okay, that's an optional model. If you look at the diagram of the protocol diagram, that part will be a dashed model. Okay, it's not a must. Okay, and for Wi-Fi. Okay, and there is a concept called distributed coordinate function (DCF). Right, so it's based on so-called interframe spacing. Okay, so the interframe spacing is something like here, right? So you have a busy channel, okay, and so here, which means previously people have been sending, right? So it's not clear, not having CTS here, okay, right? So then when this is noticed, right? So each host, each laptop, for example, they will wait for a random backup time and then start, right? So there's a different priority. So actually, there's more than these four called interframe spacing time. Okay, right? So there will be actually more than these, but these three are the most common. It's basically associated with low priority, medium priority, high priority. Okay, this is called DRFS, PRFS, and SIFS. If you are interested, you can look at the detailed concepts, but they are just the interframe spacing. Okay, and there's different spacing lengths, basically. Right? If you have a low priority one, then you should, interframe, right? Before you send a frame, you should wait for this amount of time, right? And then you try to send. And PRF is a medium priority, which you wait for a lower period of time, right? And if you are high priority, you use a SIFS. Okay, it's a higher priority. Okay, and why we have this difference, right? So you think about it. So here's an example. Okay, let's say your contention, right? So but SIF is high priority. It will try to send stuff first, right? And so then you can transmit the data, right? You sense the channel and you transmit the data. But if someone sends lower, here's the example. Okay, you sense the channel. So first the channel is busy, right? You cannot do anything. But then you wait for, because sender one may be the highest priority. You wait for less time, and then you start to enter this contention detection group, right? And then you find, hey, things are going fine, right? I get clear, right? And then I send, okay? But maybe the CTS is telling other people not to send, right? This is happening, and probably just right after these people wake up, okay? Right after these people wake up, and so they will find, hey, it's clear, right? So they cannot send. That's why they have a lower priority, right? If you wait for a small amount of time, then your priority is high. Okay, so that's the concept of this. So you don't even get a chance to contend between this interframe spacing. So because the channel is busy, then only send one succeed. So this is like they are sensing the channel. Okay, so but they find it's CTS, right? Somebody else CTS. They cannot send. Okay. Let's see. So again, so Wi-Fi is a very complicated protocol, right? So we only check the very simple stuff, okay? And those are just the concepts that you need to understand. If you really want to explore deeper, you can check deeper. Okay, there's also a scanning and a roaming concept. Let's say if you change, let's say you have your phone and you change, you connect to Wi-Fi of UAB, right? Like a UAB secure or something, right? And then you go from one building to the other building, right? So maybe from our, a university hall, right? So to some other like heritage hall, for example, right? So it's the same piece of Wi-Fi, right? So the same server basically. It's a UAB secure, right? But you are roaming, right? So you will the first wireless router will be the signal too weak. You need to switch to the other wireless router. Okay, so there's some association issues, right? So you need to disconnect from the previous one, but connect back, and then you need to have the same authentication. Right? You don't want to redo all these things like if you are new connected. Okay, so there's also technology to combat the noisy channels using different sending rate, and the infrastructure version is like our UAB secure, right? We have the wireless router. There's also ad hoc and point-to-point connector. Right? So this is because we are talking about wireless connection, right? So that could be, drones, for example, they are communicating. They have an ad hoc network. They are not connecting close to any base station or the Wi-Fi point, the access point. You don't have access to the internet. Right? Then you will first view the ad hoc network, communicate with yourself, coordinate the signals. This is also like a mesh network, mesh routing. You are not connected to the backbone, right? And there's also power saving optimization, right? So when you can go to sleep, but you will not have message loss, right? So there's some protocol, right? So because you don't want to be on all the time. If you think about it, most of the time, you are not communicating. Right? You're browsing or you are doing some processing, or then you don't have much to do, right? This is even the case if you think about this kind of mode, right? Like those very tiny sensors deployed into forest or battlefield, okay? And they want to last longer because they are battery based, and definitely they need to sleep. Like every one period, I just wake up once and get some communication signal, right? But we should have not lost any information. Okay, so how can we do that? And there's also like security encryption issues, right? If you connect to Wi-Fi and you need to do some settings, you probably already see these kind of terms. Okay, but we will not go into details. So you need to select the protocol and encryption method, etc. And so because you can have multiple causes in wireless network, so we will just cover this structured surface, right? So you just understand the hidden terminal and this kind of problem, and you understand these protocols, right? Which one is higher, right? These are all like important, but we will not go too much deeper. Okay. Next time we will come back to the Ethernet and look a little bit on the devices, like the bridge, the switch. We all know the hub, right? So, and the T connectors, this kind of stuff. Okay. I think that's all for today. I will skip attendance for today. Okay, so we will take attendance on Wednesday. Okay, so that's all for for today, and yeah, I will see you on Wednesday. Any questions? I will be here for 1 minute. If I don't get any questions, I will just let me see. Where's my mouse? Okay, thank you. Have a good day. Okay, see you. Okay, I cannot get any new information here, so maybe I will disconnect. And feel free to send me email if you have any questions. Okay, have a nice day, everyone.